Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is Independence and the Multiplication Rule. As always, I encourage you to be active learners as you watch these videos. So the topic is independence and the multiplication rule, and your objectives are to be able to identify independent events, to use the multiplication rule appropriately for independent events, and to compute at least probabilities. Let's begin with the definition. Two events, E and F, are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Two events are called dependent if the occurrence of event E in a probability experiment affects the probability of event F. Let's look at some examples. Suppose you flip a coin and roll a die. The events obtain a head and roll a 5 are independent because the results of the coin flip do not affect the results of the die toss. Are the events earned a bachelor's degree and earned more than $100,000 per year independent? No, because knowing that an individual has a bachelor's degree affects the likelihood that the individual is earning more than $100,000 per year. Two 24-year-old male drivers who live in the United States are randomly selected. The events, male 1 gets in a car accident during the year and male 2 gets into a car accident during the year, are independent because the males were randomly selected. This means that what happens to one of the drivers has nothing to do with what happens to the other driver. So, stating in other words, in determining whether two events are independent, ask yourself whether the probability of one event is affected by the other event. For example, what is the probability that a 29-year-old male has high cholesterol? And what is the probability that a 29-year-old male has high cholesterol given that he eats fast food 4 times a week? Does the fact that the individual eats fast food 4 times a week change the likelihood he has high cholesterol? If yes, the events are not independent, and not independent means dependent. Okay, so here's a problem for you to test your skills on that. So you have events E and F, and you're supposed to determine whether they are independent or dependent and sort of justify your answer. You know what to do. Let's see how you did. The first event should have been dependent. Speeding on the interstate increases the probability of being pulled over by a police officer. Part B was dependent. Eating fast food affects the probability of gaining weight. And Part C should have been independent. Your score on a statistics exam does not affect the probability that the Boston Red Sox win a baseball game. Students often confuse disjoint events and independent events. So let's talk about that a little bit. Disjoint events and independent events are different concepts. Recall that two events are disjoint if they have no outcomes in common. That is, if knowing that one of the events occurs, we know the other event did not occur, and vice versa. Independence means that one event occurring does not affect the probability of the other event occurring. Therefore, knowing two events are disjoint means that they are not independent. In fact, they are dependent. If you know one happens, the other one did not. And in summary then, two events are disjoint. They are not independent. Necessarily independent. And in fact, let's look at another example. Consider The experiment rolling a single die, and E is the event you roll an even number, and F represents the event you roll an odd number. Since these are mutually exclusive because they don't happen, and the probability of each is 1/2. However, if we were told that the roll of a die is to be an even number, then the probability of event F changes. So, the knowledge of event E changes the likelihood of observing event F. So we have a multiplication rule then for independent events, and this is only true for independent events. If E and F are independent events, then the probability of E and F both happening is the product of their probabilities. It is the probability of E times the probability of F. This is also true if you have 3 or more events. So the probability of E1 and E2 and E3 and ... and E sub n, and all these events E sub I are independent, then the probability of the end of all of them is the product of their probabilities. So let's talk about a roulette wheel. This is something that is in casinos often. In the game of roulette, the wheel has slots numbered 0, 00, and 1 through 36. A metal ball rolls around a wheel until it falls into one of the numbered slots. What is the probability that the ball will land in the slot numbered 17 2 times in a row? Well, you are saying that each of these are independent. So there are 38 outcomes, and if we get these events, 17 on spin 1, 17 on spin 2 are independent because the ball does not remember where it landed before, and that doesn't affect the probability of landing on it again. So, since there are 38 possibilities, the probability of landing on 17 is 1 over 38. And the events are independent, so that when we take the end of them, it's going to be the product. So it's 1 over 38 times 1 over 38, or 1 over 1444. If you did a calculation of this with a calculator, you would say that we expect the ball to land on 17 twice in a row, about 17 times in 10,000 tries, because that's what this number represents. Insurance companies also apply this to life expectancy. The probability that a randomly selected 24-year-old male will survive the year is this number, 0.9986, according to this report. What is the probability that 3 randomly selected 24-year-old males survive the year? And what is the probability that 20 randomly selected 24-year-olds survive the year? And we are assuming that these are independent, because there's no indication that the survival of one male affects the survival of the others. These were all randomly selected. Okay, so the probability that all 3 survive is the product of the probabilities. We multiply these numbers together and get this. Similarly, the probability that all 20 males survive is this. Now, in Part A, this meant if we randomly select 3 24-year-old males 1,000 different times, we'd expect all 3 to survive 1 year in 996 of the analysis. Similarly, down here, this is telling us that if we randomly select 20 24-year-old males 1,000 times, we would expect that all 20 to survive 1 year in 972 of the samples. Now, to contrast this, though, if 2 of the males lived in the same house, a house fire could kill both males and we lose independence. By randomly selecting them, we minimize the chance that they are related in this way. Okay, so here is another problem, and we're now going to compute at least probabilities. So we want to compute the probability that at least one male out of 1,000 aged 24 years will die during the course of the year. If the probability that a randomly selected 24-year-old male survives is this. Well, okay, so the probability that, and again we're talking about of 1,000 males, yeah, one male out of 1,000, so that's up here. So the probability that at least one dies is 1 minus the probability that none die. And if none die, they all survive. So that's 1 minus the product of the probabilities. So we're multiplying or raising 0.9986 to the 1,000th power. We do this with our calculator and we see that the answer is 0.7536. So if we randomly select 1,000 males of 24 years, 100 different times, we would expect at least one to die in 75 of those samples. Here's a problem for you to test your understanding of that. You know what to do? Let's see how you did. Well, the probability they both live to be 41 is the product of the probabilities that each one of them does because they're independent. All 5 live to be 41. You're raising that to the 5th power because you're multiplying this by itself 5 times and get this number. This was at least one in the 5 die, so that's we're talking about here. The product is the complement of the event, and so that is 1 minus this number. And it asks, was that unusual? And it is, because that is less than 0.05%, which is our threshold for things being unusual. Now we want to add this to our list of probability rules that we've been assembling. And notice that previously we talked about or, but now we're talking about and also the law of the complement as well. So the probability of E complement equal 1 minus the probability of E. And if E and F are independent events, then the probability of E and F equal the probability of E and the probability of F. Or means addition and tends to imply multiplication if we're talking about independent events. In closing, now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.